Um, and if I perhaps ever want you to like delete the video on YouTube, I'll tell you, but that probably won't happen.
Mm, sure.
Um,
Okay then. Yeah.
Today I'm going to like ramble about a few things I was thinking about in the shower just a few minutes ago.
Oh,
Um,
cool.
uh, so I was thinking about a bunch of things. Uh, okay. So I was thinking about, so let me just start off by by talking about this inner space.
Hmm.
I'm not sure if what I'm
Oh,
writing.
I
Oh, it
see
is.
you. Yeah. Okay.
Um so I'm not going to go into the details, but it is but I am going to draw. Oops, I left the room. Let me get back in. Okay, so I'm going to like draw. Hold on. Okay. Where was I? Okay, so I'm going to draw the Penrose diagram of the Zitter space.
Hmm.
Which you can draw is a square, and I'm going to explain this. So assume that this is d-dimensional de Sitter space. We have time and we have space. Uh, in the case of space, because the space uh is in this Penrose diagram. Um, S d minus one. So it's like a d minus one dimensional sphere. Um, so if you have a sphere, for example, let d equals 2, then it's basically a spherical shell. Um, and you have the north and south poles, right? Let me just draw them. So you have the north and south poles. Then this drawing is basically the north pole is here and the south pole is here. Um, so these are points, and every section in the middle is actually referring to SD minus 2. So it's basically like follows. You slice it.
Sure. So basically, the drawing on the left is basically a two-dimensional de Sitter space, right? So the
Uh,
the one sphere is just a line segment.
right. Well, this is a dimension for d-dimensional de Sitter space, but like it is basically it's a Penrose diagram. So we are um
Yeah, sure. I think I understand.
yeah, we are
Yeah.
projecting out a few spatial dimensions.
Mm. Okay, that's good.
And like what you can draw two light like null lines here. These
Mm.
two lines are null. Um, the interesting thing here, if you so you can actually write down the metric for this. I'm just gonna write that down because if so, basically by this drawing, you can basically tell what the topology of the spacetime is, but like you would definitely also like want to know what the metric is. So let me just write that down for reference because that will make people happier. Let's see here. The metric. What is the metric? Let me just write it down. The metric is equal to ds squared is equal to minus dt squared L squared cosine hyperbolic squared T over L d omega square d minus 1. So this is the part that is basically SD minus 1.
Mm.
Um,
Sure.
and this is the time coordinate. Um, So what we see here, if you return to the Penrose diagram, is that you have you have a line in the future and a line in the past. And you can check that it takes you an infinite amount of proper time to reach this point. Let me check that in terms of calculations. So imagine if you start at t equals t0, and basically the line up here is actually t equals infinity. The line over here is t equals minus infinity. So the proper time it takes you to get from t0 to infinity is infinite. I don't this is clear from the metric, I think. Um and
Sorry, I'm not too familiar with why it's clear.
because it's minus dt squared.
Okay. And okay, sure, sure.
Right.
Yeah, okay. Mm.
So and also if you go to t equals plus minus infinity, you see that due to this scale factor, space is like expanded.
I see. Oh, so basically
So
ds
over
squared is minus d tau
t
squared,
equal,
right? Would this be right? To
yeah,
okay, can.
yeah.
And this term, how about this
So
cosine
basically,
term?
so uh let's just assume that the radial the coordinates d minus one remains constant while we're moving.
Okay, sure. All right.
And like so basically at the very top and the very bottom of the Penrose diagram, space has become infinitely expanded. Um,
Hmm.
space and time has been infinitely expanded. In terms of time, that is because obviously it the small t coordinate runs from infinity to minus infinity, but we like fit it all into this diagram, so it has
Hmm.
basically it has basically been
Conformally.
yeah, conformally contracted a bit.
All
So
right.
yeah, so keeping that in mind, you should understand these top and bottom boundaries as something being at infinite time where space is infinitely expanded. Um,
You happen to remember the conformal mapping at the top of your head, like du squared and dv
I think
squared?
yeah, I think you can work it out yourself, but let me
Okay,
show you how I would do that.
sure.
Um, so I will try to create a situation where ds equals some function of u and du squared plus d omega d minus one squared. This is what I would want, I think. Um, and the thing to note here, um, is
So u is a function of t, right? As in u is the
yeah,
essentially
u is
the
a function
okay.
of t. U is
Right.
a function of u is a function of t. And the way I would do this is I can tell that fu is equal to L squared cosine hyperbolic squared. Let's call it L squared u because why not?
Hmm.
T over L, and we see that fu du is equal to dt. Um, so
Hmm.
plugging that in, we see that du is equal to L cosh t over L dt, and then we integrate both sides to get the result.
Ah, okay, cool.
I'm going to skip that, and
Hmm.
so basically, one interesting thing here, uh, so you have to really use your mind. So I'm going to look at another specific coordinate system. And the way this coordinate system works is basically, I'm going to draw a few lines here. So this is how. So I'm going to draw a few lines first, and I'm going to write down the coordinates in this coordinate system before I explain anything more. Let's see here. Um, right. This is ds squared equals dt squared plus e to the 2t over L dy squared. This is the metric, and I drew the const t surfaces. So here I drew the const t surfaces, and over here is t equals infinity, and over here equals t equals minus infinity.
On the diagonal line or on the diagonal line is t equals minus infinity.
Yeah, the diagonal line is t equals minus infinity.
Okay, that's
Um,
interesting.
now a few things to check here. Is that as t goes to infinity, right? Space becomes infinitely expanded,
Sorry, I'm a bit
and
confused about this diagram. Is the vertical axis the y-axis and the
no, this
or
is the diagram from above with this being t
oh
and this
okay.
being it's the same
Yeah.
diagram.
Just that you rewrite the metric in this new coordinates, and
Yeah,
it turns out in this new coordinates, these are the constant t lines. The
yeah,
okay. Is there a name to
uh,
this metric
yeah.
you
This is called the flat slicing.
interesting? Okay.
And the thing here to note here, is that when you have so the thing to note here, let's look at each const t surface, and see how it works. The structure of each const t surface basically contains the south pole, but basically is open over here at the north pole. So what it basically looks like is dot 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 dot. Here is the south pole, and it stretches out. And it's not compact. It's not compact, and it has the topology. It has the same topology as RD minus one.
Hmm.
So this
Okay.
makes sense. So we see that Y is just in RD minus one.
Um. Sorry, when you say dy squared, right? Does y refer to the d minus one dimensional sphere? Or
It's not a sphere, but it's a plane.
I see. So y is basically a vector of many components, right? Y
Yeah,
is the so if I expand dy, it'll be dy one squared plus dy two squared
yeah,
and so on. All the
yeah.
components.
Let me rewrite this. So
Okay.
basically, the each const t surface has the topology of SD minus one minus the North Pole,
Okay. Okay.
which is topologically equivalent to RD minus one.
Hmm.
I just wanted to point that out. And
Sure.
so let me tell you about some phenomenon that is interesting. So let's say that we start out at t equals t zero, at large t equals large t zero, and some point.
Hmm. Yes.
Um, right. The Let's see, there's and assume that you, for the sake of argument, send out um a light-like signal with a light-like signal.
Mm-hmm.
Um, Now we want to discuss something that is analogous to proper time for a null line, but null lines don't have proper time, so instead you need to come up with the concept of basically an affine parameter.
Mm-hmm. Well, I think Witten talked about this before. Like he constructed essentially so-called geodesics for lines.
Yeah,
So something he said like was for time like stuff is like the geodesic minimizes or extremizes the proper time, and then
yeah,
uh, the other one is minimized, and then like is like I forgot the term he used, but yeah, he constructed some nice stuff around this.
yeah. But for our purposes, we will just need to keep in mind that there is this affine parameter. So we see that we have this affine parameter which we're going to call lambda, and the velocity vector we will call k, and the affine parameter is defined such that along this null geodesic we have nabla k is equal to 0. Or to write it differently, kb nabla b k 0. Hold on, null geodesic. Or to write it differently, we can have a field day with this. You can see that dk, we can write a dk d lambda plus Okay, A, B, C, K, A, K, B, K, C. Wait. Yeah, K, B, K, C. So that is the definition of an affine parameter. And it's basically analogous to proper time. Uh,
The affine parameter is it can be redefined up to a fine transformation, right?
right.
Okay. Sure. Then mm, okay, yeah, go on, go on.
Right. And let me see. Yeah. So the thing that's interesting here, is that you start from t equals t0, right? And you get to t equals minus infinity, infinite affine parameter.
Mm-hmm.
And the way you can check this is if you go back to the original Penrose diagram, you can obviously try to calculate this yourself. But if you go to the original Penrose diagram, you see that the start points and the end points are two really non-singular points in de Sitter space. In fact, there is an isometry that turns one point into the other point. So basically, both of these points are really just very typical. There's nothing weird about any of these.
Mm,
Um, so the affine parameter distance between the two must be finite.
mm,
There's nothing weird with either of these. And the fact that t equals minus infinity at the endpoint is just a feature of the coordinate system.
mm. But
So
then
it's
the affine parameter can be redefined up to a scale affine transformation, which includes scaling. So, like, how do we even assign a specific affine parameter
well,
to?
if you do an affine transformation on a finite number, you get a finite number.
Okay. Right.
So the
Okay.
fact that
Sure.
it's finite doesn't change.
Sure.
Um, and this is really interesting because assume that you are thinking entirely in the perspective of the flat slicing observer. So you have t equals t0, and you're just standing there, and you know for a fact. Wait, I went down, and you're just standing there, and you know that the universe is expanding. So you're in an expanding universe right now. Um, and you extrapolate basically that the universe is expanding exponentially, and so if you go into the past, it would be the universe will be basically crunching exponentially,
Wait,
but it
sorry.
still
The how do we know that the universe is expanding exponentially? Is it from de Sitter space? Is that a property of de Sitter space?
no, it's just it's just the metric, right? It's e to the e 2t divided by L.
Oh, okay. So
That's what I'm
this.
talking about.
Oh, I see. Sure. All right.
So we know that the universe is expanding exponentially. That's cool. But like time still existed infinitely far into the past, right? Assume we have
Hmm.
this not necessary. It's not a geodesic, but assume we have a const y line.
Mm-hmm.
Um, then according to the metric, we can make this line as long in terms of proper time as we want. This can go as long as we want into the past.
Hmm.
Uh, but for some reason, oops, I accidentally left. Let me get back in.
Uh, just to clarify a bit on the universe expanding part, right? When
Yeah,
you say look at the metric, it's because if we have two tangent vectors, as you see over time, the longer time parameter runs, the t, then the larger the value you get for the, let's say, the dot product of the two vectors. That's how we know, um, yeah, that's how we know distances.
I
Is
I think I think I'm saying that the universe expanding. And I'm saying that because the universe, as expressed in this particular metric, is an FLRW universe, and there is more or less a definition for what it means for a universe to expand in an FLRW universe. In this
I
case, it's
see.
kind of obvious because like it's the scale factor increases in time. That's what I meant.
I see. I see.
Um,
Is this similar to how they like model the universe in cosmology? So I'm not too
yeah,
okay. Cool.
this is a model of the universe where you have inflation.
I see. Okay.
But you don't need to remember that. And what's interesting is that if you send a light signal, it somehow leaves the space-time
Hmm.
in finite affine parameter, which is very weird. Like consider just flat space, which isn't expanding.
Hmm.
But time runs infinitely far back into the past. And if you send a light signal, this thing will still stay within the space-time for an infinite affine parameter.
Hmm.
Um, but in this case, it's not, which is very weird. Um, if you think about it, well, it's not weird at all. It's very clearly explained. But it's not. It's different from flat space. So the question is, how would you explain this? Well, you don't necessarily have to explain it. It's just is what it is, and it's not implausible. But you can actually think about it from the perspective of Penrose's singularity theorem.
Oh.
Um, um, So I'm not going to prove the theorem. I'm just going to state it and do a sketch of how you would go around proving it. Um, so Penrose's singularity theorem states that it makes a few assumptions. So the first assumption, P1, is that you have what is called the null energy condition, which is basically equal to saying that, let's see here, um, RAB KA KB or KA equals 0, so it's null, is, let me check,
Is K
larger.
is K still defined as the parameter as a vector along the geodesic?
Sorry?
Is K still defined as the vector along the geodesic?
No, K is just a null vector. Let me just write something else then.
Oh, okay, sure. Oh, okay, I understand now. Yeah. Okay.
For the sake of things, I'm gonna call it U. Um, so this is just a condition on this is a condition on the Ricci tensor. Um, and you have the second um assumption that you need, which is very important. This is extremely important. The universe has a non-compact Cauchy surface. So, example, so you can have a Cauchy surface sigma Cauchy, which is topologically equivalent to Rn, Rd minus 1,
Hmm.
but you cannot have a Cauchy surface that is topologically equivalent to
SD.
SD minus. This is not
Okay,
okay.
cool. So like we cannot apply this to radio quantization schemes where you cut the universe in spheres.
Yeah, that is not okay.
All right.
Which is interesting. Let's see here. And the P3 is basically the crux of P3 is and so like P1 and P2 are basically like conditions for the whole proof to work, and P3 is like the real deal, the real input, and it is basically that you have a compact there exists a compact trapped surface.
I've tried studying trap surfaces, but they're still way beyond me. Yeah.
Yeah, I guess, but you can understand the definition, so I'm just gonna work on
Mm.
that right now. But like, I just want to state in P2, you are basically saying that the universe has a compact Cauchy surface, but you're basically saying that the universe has a Cauchy surface, that is included in the statement. So obviously, the universe has to be globally hyperbolic.
Mm.
So in case of P3, it's very, oh, by the way, it's very rare in relativity that you would deal with a non-globally hyperbolic universe. But anyway, there exists a compact Cauchy surface. No, a compact trap surface. So let me just explain what that is. So, so if you have a d-dimensional spacetime, a trap surface is a d minus 2 dimensional surface. That is defined um as so. Let's see here. Uh, let me check.
Do you have any
So,
very good
so
resources
if you could,
for?
it is a space-like surface,
Mm.
which is basically saying that if you have 2 points, uh, on the trap surface, they are space-like separated.
All right, sure.
Um, and they satisfy the property such that on every point on the surface, you would you would define two null. You would define ingoing and outgoing orthogonal null geodesics, which are basically
Mm.
so they are like there's two of these. There's one here. There's one here. These are respectively ingoing and outgoing. So these are null geodesics.
How do you determine which one is ingoing and outgoing?
Uh, well,
Wait, it's more like a cone, right? Oh, but then it's d minus 2, so the codimension is
it doesn't really matter.
all right.
It won't matter much in our argument. But like, there's two.
Sure.
So these are, that are, if I recall correctly, or the. Let me check. Um,
Well, you probably define them with respect to the orientation of this manifold. Probably, I'm guessing.
yeah, but
Yeah, okay,
yeah,
sure. But it
because
doesn't
like
really.
if one of the directions goes in, well, yeah,
Mm.
do it however you'd like. And okay, let me just check something real quick. All right, okay, that are orthogonal to the trap surface. So yeah, they are orthogonal as so.
Mm.
And so because it's a space-like surface, so if you go locally, if you look at this locally, what it would look like is that you could basically assume that it's like if you go locally so that it looks flat, um, you can assume that this local part of the trap surface that is space like so. It's basically there's one time coordinate, there's one x coordinate, and there's a bunch of y coordinates that are space like is basically equal to x equals fixed. You can locally you can see that so there are d minus 2 y coordinates. So you can locally if you go into local if you look at this locally infinitesimally locally you can see that the local part of the trap surface is basically equal to x equals fixed. In some sense you can choose a coordinate system that is so that it is like that, and now you have two null geodesics that start at this point that are orthogonal to the y coordinates. So therefore, they will not have any y components. Yeah, they will not have any y components. So they will only have x and t components. But then you get two fixed possible directions in which the null geodesic could go, which is basically equal to dt d lambda equals plus minus dx d lambda. So one of them will be ingoing and outgoing, and the other will be outgoing.
I see.
So you see that you have these two null vectors that are shooting out at every point. And we can define theta. So at every point you have two null vectors, and they can be classified as ingoing and outgoing. And you define theta as mm, you can define theta in many ways. Let me see which way will be the most intuitive. You can define theta as basically defined by Ka delta A. It's theta delta A, where delta A is infinitesimal volume on trap surface. So let me explain. So assume that you follow either for the ingoing or the outgoing null geodesics. You follow the geodesics, and then the trap surface will evolve a little bit, right? And a minuscule and an infinitesimal volume element will have its volume changed if you follow this change. And so basically this is the volume change.
I see. How do you define the covariant derivative of that infinitesimal element? A differential form. Oh, okay, right.
Yeah,
So
you
it's
can do it using a differential form and taking
okay.
the covariant derivative of the differential form. That's totally cool.
Oh,
That is the kosher way to do it. And theta is defined as basically so if theta is larger than 0, right? This is expansion. And if theta is not less than 0, this is equal to shrinking, I guess. Yeah. So what do we mean by a trapped surface? So a trapped surface is basically one for which both the ingoing and the outgoing directions. You note that theta is basically defined on every point of the trap surface. It's a function of your position on the trap surface. A trap surface is such a surface with a bound theta less than lambda for both ingoing and outgoing.
I see. Why do you need to be? Why can't it be just less than 0? Is that enough?
0 is not enough. This thing has to be finite. Some finite number.
Oh, some finite number. So this lambda is nothing to do with any parameter. Okay, sure.
Yeah, so yeah, because it's not, so yeah, we don't need to call it lambda. So instead I will call this weird thing.
Oh,
Now it's a cool n. But like
oh.
yeah.
But if it is some finite number, then isn't it just strictly less than zero? Is that not enough? Or we are trying to discount infinitesimals?
Yeah, we're discounting infinitesimals.
If you mind elaborating, why do we want to do that? Like, to me, it seems intuitively.
Yeah, I can explain. So we
Okay,
will
cool.
see that this number appears um in the result of the theorem. And if you take that to 0, then the theorem isn't as useful.
I see.
Yeah, we'll get there very soon.
Okay, cool.
So I think like what these three propositions are what are the necessary assumptions for for Penrose's singularity theorem. Um, I would like to emphasize that for all practical purposes, the first proposition, which is the null energy condition, is important. The second proposition that the universe is a non-compact Cauchy surface is also really important and should not be forgotten. And the third proposition is basically, um, I guess, the juice of the theorem. But like, yeah. So from here, you can see the result is P4. The universe is geodesically incomplete.
Hmm. Meaning that geodesics end somewhere, right? They cannot be
Yeah,
continued.
I can explain this, and what I mean by that is, mm, what I mean by that is, um, hold on a second. Um, so you have the trap surface, and you have all the um, okay. What I mean by that, mm,
I'm guessing the metric would blow up at some point in the geodesic, but I could be wrong.
well, not exactly, but like, let me
Okay, cool.
explain. We're just checking. Uh, the thing is, um, right. So for all the geodesics that are all the ingoing and outgoing geodesics, that are coming out of this surface, um, at least one geodesic, hold on. Right. Mm. So yeah, so basically there is at least one geodesic uh, ingoing or outgoing, uh starting at the trap surface that um is wait that is inextendable in the spacetime, and let me explain what I mean by that. Um, so what I mean by that, is that, for example, if you consider flat space, in flat space, you wouldn't have this situation. If you consider just some surface in flat space, it's not going to be a trap surface.
Mhm.
It's not a trap surface. But we can see whether or not the geodesics are inextendable. So for if you have just if the trap surface is just a circle and you have geodesics that are going in these two directions, which are respectively ingoing and outgoing, we see that, well, they can just keep on going for as much as they want. Um and so we see that these are both extendable. Um and by extendable, the definition of extendable inextendable means that hmm uh let's I don't recall the definition, which is annoying. And I don't
It's
seem
okay,
to have
take your
written.
time. You can
Yeah.
Google if you want.
Well, mm, Okay. So as it turns out, this is actually quite simple. Um. Dum 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 dum. Hmm. By inextendable. Check. Hold on a second. Hmm. See. Hold on a second. Okay, so inextendable is not the right word for this situation. I think
Sure,
let's
sure.
just yeah, dude. So what I
Incomplete?
really
Oh,
want to say, what I really want to say is actually pretty simple. Um, I just want to say that the universe is geodesically incomplete. Um, if so, what by geodesically complete is that I mean that for any geodesic null null geo so but by null geodesically complete I mean for any null geodesic in some affine parameter we can continue it from arbitrarily small affine parameter to arbitrarily large affine parameter. So you can continue it from minus infinity affine parameter to infinity affine parameter. Um, for any null geodesic, we say that the universe is
mm.
null geodesically complete. So for null geodesically incomplete, we mean that there is some null geodesic which cannot be infinitely continued either to the future or to the past.
Usually, what's the condition that makes them fail?
Hmm?
Usually, what's the condition like they hit a point where perhaps the point is a
You hit a
singularity or
singularity, or
okay.
something that isn't a singularity at all. So if you go back to the original
I
de
suppose
Sitter case,
it's a real singularity, right? Like not a coordinate singularity.
well, it might not actually be a real singularity.
Oh,
If you go to the de Sitter case, just a sec,
okay,
it
cool.
does not necessarily have to be a real singularity. That is not proved by the theorem. But if you go into the de Sitter case, if you go to the Penrose diagram I drew above, um, yeah, over there, below that, yeah, that one. You can see that this is actually true. Um, See, this null geodesic that I drew over here, this is the one that cannot be continued beyond a certain affine parameter in the past because it leaves the particular patch we're talking about.
I see. So geodesically complete is a property of a metric in some coordinate system. It could be dependent on the coordinate system.
Well, no. And this is the tricky part. Um, I just want to emphasize that uh, by this metric, so by space-time, by the flat space in space-time, I'm just talking about this patch over here that I've illustrated here.
Ah, I
That is
see.
the space-time
I see.
that is described by this metric, and there is something that I guess you could call a trap surface. Well, yeah, you'll have to, yeah, this is a trap surface, and these are the
Hmm.
ingoing and outgoing geodesics.
I
Um,
see.
and it's really quite strange. Um,
I see. So this
but it's
triangle
not.
over here that you draw in the top upper left that shaded, It's a trapped
Yeah,
surface.
yeah, it is a trapped surface. And um so let's just try to check like if all of the required prerequisites
Mm,
for the singularity theorem are hold here.
mm,
Number one, the null energy condition is indeed satisfied for this center space. You can calculate
mm,
that it is so. And number three,
mm.
we have a trap surface, which is the one over here that I've just circled. The question is, do we have a non-compact Cauchy surface?
Wait,
Now, if you
sorry,
go
how do
back
we know that this is a trapped surface? Like the geodesics, the null geodesics, they are,
volume uh, compressing, volume shrinking, you can check by calculation.
is it
Um,
due to this expanding universe factor or
yeah,
okay, sure,
more or less. You can calculate this, but I don't think I have the time to go to the details today.
sure.
But the cool thing here, um, the cool thing here is that like this particular patch, in fact, does have a non-compact Cauchy surface. Because the Cauchy surface is topologically equivalent to RD minus one.
Hmm,
Each const T surface is a Cauchy surface.
I see.
But like if you were to consider the whole de Sitter space spacetime, then the Cauchy surface will be compact because it's a sphere.
Sure,
So you see that by restricting our attention to this patch with the flat slicing, that is actually the key. That subtlety is actually really important.
I see. Okay, that's interesting. So if we didn't restrict it to this, then um the we could have which condition breaks if we didn't restrict it to those
P2.
P2. I see. Would P3 still hold? Would the Cauchy surface for
Yeah,
um
P3 still holds because Akashi's because the being a trap surface doesn't yeah, it's just a local calculation.
is it true that for every de Sitter space there is a trap surface?
Yeah,
I see. Okay, I was under the impression that trap surfaces are things that kind of appear in black holes where the metric is there's some like event horizon thing, but for de Sitter space it's more of like we live in a de Sitter space universe, right?
well, we used to
We used to.
actually. So yeah, I actually know a little bit more about this than I used to, but we used to live in the De Sitter universe, but now things changed because inflation stopped. So in the far
Oh,
future, before inflation stopped and reheating happened, we used to live in the De Sitter space.
I see, I see. So okay, I'm perhaps my intuition is wrong, but is it right to say that inside a black hole is anti-de Sitter space, while outside a black hole is roughly speaking de Sitter space? Or is my intuition very misguided?
I'm not sure. Um, yeah, I'm not sure.
I see. So okay, okay, cool.
It
Uh,
depends on the case, but yeah, I'm not sure.
cool. So the explanation for the unintuitive behavior of this now geodesic possibly hitting the the boundary of the universe in some sense
Yeah,
is is basically the statement that the now geodesic cannot be it is not geodesically complete.
yeah,
I see. Interesting. And this is also this happens because we restrict ourselves to this subspace, right? If we
right.
perform the procedure on the whole space, um we would not see this now geodesic hitting the boundary of space kind of thing.
Yeah, because it'll just keep going.
I see. I see, I see.
Um,
Is there a way to patch multiple of these triangles together to form the whole space? I'm imagining like four triangles or three triangles.
yeah, let's see how I think like how much will we need? I think like if we take this one and this one and this one and this one. Yeah, if you take
Yeah.
like four, that would be more than enough. Um, but yeah, you will need multiple. Um, but like okay, I just want to get to the final point of what I was talking about.
Okay, sure.
Why like all this was just came to my mind and I'm just scrolled to the bottom now. Um all this just kind of came to my mind. I don't know why, but I was suddenly intrigued by this. But maybe I should explain this next time because this is a can of worms. I'll get back to this
Sure.
next time. This
Okay.
is something that just hit my mind. I would like all of this to be private though.
Okay, sure.
Because
Is
it's
it related to
possibly
your research?
maybe, and that's why I'm kind of scared. Okay.
Okay,
Well, not
sure.
only tangentially, and possibly it will not be related at all. But I just want to keep all this private.
Sure. Understand.
Okay,
Okay,
so see
cool,
you next
cool.
time.
See you.
Have a
Thanks.
good day.